Okay, let's get right into a core challenge in machine learning. I mean, building a great model is tough enough, right?
Definitely.
But knowing how much you can trust its predictions, figuring out the uncertainty, that's often even harder.
Oh, absolutely. And it's essential, really, for any real-world use.
Like what kind of things?
Well, think about needing a medical diagnosis recommendation, maybe,
Uh-huh.
or a personalized financial forecast. You don't just want a single guess.
No, you need more than that.
You need a range of possibilities you can actually rely on. Ideally, with some kind of formal guarantee.
Right, and this is where this framework called conformal prediction comes in. It sounds pretty powerful.
It is. And one of its biggest pluses is that it's distribution-free.
Meaning
It doesn't have to make big assumptions about let's say, the complex shape of your data.
okay, and its core promise.
Its fundamental promise is incredibly appealing, actually.
Yeah.
You give it a new piece of data, right?
Mhm.
And it can produce a prediction set.
Like a range of values, or maybe
Yeah.
a list of possible labels.
Exactly. And that set is guaranteed to contain the true outcome with the specific probability you set beforehand, say 95%.
Wow, okay. A guarantee, but there's a catch.
Well, the guarantee holds, crucially, if your data is exchangeable.
Exchangeable. What does that mean, basically?
It essentially means that the data you use to calibrate it and the new data point you're testing are, statistically similar, coming from the same kind of process.
Gotcha. So how does it actually do that? How does it make this prediction set?
It relies on a separate batch of data where you already know the answers. That's your holdout calibration set.
Okay, so you need some known data aside.
Yes. You feed this calibration data through your model, and you compute something called nonconformity scores.
Nonconformity scores. Sounds a bit technical.
But think of them as just measuring how weird or unexpected each calibration data point looks compared to what your model predicted for it.
Okay, like an error score, but maybe more general.
Kind of, yeah. And you use these scores from your known data to figure out a threshold.
A threshold.
Right. Then for a new point, anything that falls below that weirdness threshold gets included in your prediction set.
Ah, I see. It sounds quite elegant.
It is. But here's the big problem, and it's pulled straight from the research paper we're digging into today.
Okay, what's the catch?
Standard conformal prediction really hits a major wall when that real labeled calibration data is scarce, when you don't have much of it.
Right. Scarce labeled data, that's a common headache. So what happens then?
Well, the prediction sets you get can become totally useless. They might be overly cautious, including almost every possible outcome.
So not helpful at all.
Or, non-informative. The paper gives a really stark example, actually.
Oh, yeah.
If you want to miss the true answer only 5% of the time, that's your alpha of 0.05. Pretty standard. You actually need at least 19 calibration points.
19? Just to get anything useful.
Just to get a prediction set that isn't completely trivial, yeah? Below that number, it might just shrug and say, well, your outcome could be anything from A to Z.
Wow. Okay, that's not very practical if data is hard to get.
And this isn't just some academic thought experiment. Think about real situations where getting labeled data is inherently difficult or expensive. Personalized medicine, maybe, where you need reliable predictions tailored to a specific patient's unique characteristics. Or ensuring fairness guarantees for small, underrepresented subgroups in your data.
Right, you just don't have hundreds or thousands of labeled examples for those niche cases. It's a real bottleneck.
Exactly.
Okay, but there's a flip side here, right? That's what makes this deep dive interesting.
Yes. While labeled real data is hard to get, we've seen just mind-blowing progress recently in training powerful machine learning models, even with limited real data.
Yeah.
Largely thanks to our ability now to generate amazing synthetic data.
Ah, data created by AI models themselves.
Right. Modern generative models can churn out data that looks and feels remarkably like the real thing sometimes.
Okay, so that leads us to the core question. This paper we're looking at, it's from authors at Technion and the University of Pennsylvania, right?
Correct.
And their central question, which is kind of the mission for our deep dive today, is can we take all this abundant synthetic data?
Which is all and much easier to get.
Right. Can we use it to sort of supercharge conformal prediction, make it more efficient, give us a shortcut to better prediction sets?
While still keeping those rigorous, ironclad coverage guarantees.
Exactly. Can we get the best of both worlds here? Use the easy-to-get synthetic data without losing the trustworthiness.
And their answer, perhaps unsurprisingly given the paper exists, is yes. They propose a framework they call synthetic-powered predictive inference, or SPPI for short.
SPPI, okay. So this SPPI framework needs to figure out how to use potentially huge amounts of the synthetic data effectively, even though, crucially, that synthetic data's distribution might not perfectly match the real-world data we actually care about. That sounds, well, tricky.
It does, yeah, and the core idea that makes it work is quite clever.
What is it?
That's where the key innovation lies. Something the authors call the score transporter.
Score transporter. Okay, what does that do?
Think of it like a translator. Its main job is to map a nonconformity score. Remember that weirdness score?
Yeah.
Calculated from your trustworthy but limited real data. Map that score into the equivalent space of scores calculated from your much larger, maybe less trusted synthetic data.
Huh. So you're taking a weirdness score from the real world and figuring out what that same level of weirdness would look like if it had come from the synthetic world instead.
Precisely. That's the intuition. And the really clever part is how it does this mapping.
Oh.
It doesn't need you to make strong assumptions up front about how similar the real and synthetic data distributions are. Not for the guarantee to hold, anyway. It actually builds this mapping using the calibration scores from both sets, the real and the synthetic.
Okay. Help us visualize this a bit. How does this transporter actually fit into the prediction process? You get a new point you want to predict.
Right. So at a high level, SPPI still calculates nonconformity scores. It does this for your small real calibration data and for your big synthetic data using some fixed model or scoring function.
Okay.
Then, when you get a new test point and you want to see if, say, a specific label Y should be in its prediction set, you calculate the nonconformity score for that test point paired with that potential label Y.
Right. Standard conformal prediction stuff so far.
Exactly. But here's the twist. Instead of comparing that test score directly to the threshold derived only from your small real calibration set,
which we know might be unreliable.
Right. SPPI applies the score transporter to this test point score first.
It translates it.
It moves the score into the synthetic score space.
Ah, okay. So you're not directly using a raw synthetic scores to set the threshold for the real test point, but you're using them to define the space you compare against after you've translated the real test score.
Exactly. That's the key. You compare the transported test score to the empirical quantile, basically the threshold derived from the scores of your large synthetic calibration set.
Got it.
If that transported score is below the synthetic threshold, then the label Y gets included in the prediction set for your test point.
Okay, that makes sense. It feels like you're leveraging the sheer volume, the muscle of the big synthetic data set to get a more stable, more informative threshold. But you're making sure that threshold is applied correctly back to the real-world test point via this transporter mechanism.
You've got it. It's like using the synthetic data's statistical power without being fooled by its potential distributional differences from the real data, thanks to the transporter calibration step.
And presumably this can be computed efficiently?
Yes. The paper shows that it can be done efficiently, which is obviously important if you want to use it in practice.
Okay, good. Now, let's talk about those guarantees again. You mentioned keeping the rigorous guarantees. Can we really trust this? Especially if the synthetic data isn't a perfect match for the real data? That feels like the critical point.
It absolutely is. And this is honestly one of the most surprising and powerful findings from the paper. It's where the theoretical results really shine. They provide two main types of guarantees.
Okay, what's the first type?
First, let's imagine the ideal case. Your synthetic data is actually pretty similar distributionally to your real data.
Like if your generative model is just top-notch, or maybe your synthetic data source is inherently very related to the real task.
Exactly. In that good scenario, the actual coverage you achieve with SPPI, the chance of capturing the true outcome will be very close to your target level, that 1 alpha you set.
Makes sense.
The paper shows precisely how tight this bound is, and it depends, as you'd expect, on how similar the distributions are. And here's the key part for efficiency. If you have a lot more synthetic data than real data.
Which is usually the whole point.
Right. The paper proves SPPI's bound is tighter, meaning potentially smaller, more informative prediction sets than what you could get with standard conformal prediction using only your limited real data.
Ah, so you really do get that efficiency gain you were hoping for when the data aligns well. Better synthetic data helps you get tighter prediction sets.
Exactly. That makes intuitive sense. But the really powerful guarantee, the one that made me sit up, is the second one.
Okay.
What if the synthetic data is not close to the real data at all? What if there's a significant distribution shift that maybe you didn't anticipate or couldn't fix?
Yeah, that's the big fear, isn't it? That your predictions will just fall apart because the synthetic data led you astray.
Standard CP, if you naively used only synthetic data, would likely fail its guarantee in that case. But SPPI, it provides worst-case coverage bounds.
Worst case bounds.
Yes. These bounds depend only on the number of real calibration points you have and the number of synthetic points you use. Crucially, these bounds hold regardless of the relationship or the shift between the real and synthetic data distributions.
Whoa. Hang on. So you're saying there's a guaranteed safety net? You can know for sure, mathematically, that your coverage won't drop below a certain calculated level, even if your synthetic data turns out to be surprisingly bad or different.
Precisely. That's the robust guarantee. You can set a guardrail. Maybe say, I need to guarantee at least 80% coverage no matter what. And SPPI, based on your amount of real and synthetic data, can tell you if it can meet that, and it will provide at least that minimum coverage, even if the synthetic data is quite different from the real data you'll encounter at test time.
That's incredibly powerful because distribution shift is so common in the real world and often hard to quantify.
It really is. It gives you a level of robustness that's very valuable.
And the paper mentions these robust bounds still hold even if the way you generated or maybe selected your synthetic data somehow depended on looking at your real data first.
Yes, that's another key point, which gives you amazing flexibility. It means you can actually try to improve your synthetic data pool. Maybe you select subsets of synthetic data that look more relevant to your small, real data set based on some criteria. And doing that selection doesn't break that fundamental worst-case coverage guarantee. The guarantee just adapts based on the size of the data you actually use.
Okay, let's dig into that a bit. How do you actually try to make the synthetic data more helpful within this SPPI framework while keeping that safety net?
Well, as we just discussed, better alignment between the real and synthetic scores improves the efficiency, right? It leads to tighter, more useful prediction sets closer to your target coverage.
So you want them to be similar, if possible.
Exactly. So one strategy is to actively try and make the synthetic scores look more like the real scores distributionally.
How would you do that?
You could potentially learn a function, maybe another small model, to adjust the synthetic scores, or perhaps even use a different scoring model specifically trained or adapted for the synthetic data to make its scores behave more like the real ones.
And the paper confirms you can do this kind of adjustment, even using your limited real data to help guide the adjustment. And you still keep that robust worst-case guarantee.
Exactly. That's a really important finding. The guarantee holds, you just might get better performance on top of it.
Okay, that's one way. What's another strategy?
Another strategy is, instead of adjusting scores, you select a subset of your available synthetic data. Maybe you have a huge pool of synthetic data, maybe from various generation processes or sources.
Right.
You could try to pick the synthetic data points that you think are a better match for your specific limited real data.
Like intuitively picking the synthetic points that are closest or most similar to your real ones.
Yeah, something like that.
Yeah.
The paper describes a specific strategy using k-nearest neighbors, but based on score distributions. You might identify groups or clusters within your synthetic data, and pick the group whose score distribution looks most similar to your real data score distribution.
Okay, interesting. Focusing on score similarity.
And the great thing is, even though you might be picking a potentially smaller, more curated set of synthetic data this way, the robust coverage bound still holds. It's just calculated based on the size of the subset you ultimately choose to use.
That makes sense. So you're essentially trading off maybe the sheer volume of the entire synthetic set for potentially better alignment with your real data, hoping for tighter sets. But you still keep a formal promise based on the size of data you ended up using.
Exactly right. You maintain the guarantee.
Okay, so this all sounds great in theory. They tested this out, right? What did the experiments show?
I think they looked at image classification and some kind of regression.
They did. They set up experiments pretty carefully. Typically, they'd have a small real calibration set, a larger synthetic set generated somehow, and then a separate real test set to evaluate on.
And they compared SPPI too.
They compared against standard conformal prediction using only the small real set. They also compared it against trying to use only the synthetic set for calibration, which you wouldn't expect to work well if there's distribution shift. Right, that's kind of the baseline failure case you'd expect.
Exactly. And they looked at two main things. Did the method actually control coverage, get the target guarantee? And, importantly, how informative were the prediction sets or intervals? Were they small and useful? or huge and vague.
Okay. So on ImageNet, using images generated by AI models as the synthetic data, what happened?
Right. So they used, I think, just 15 real calibration points per class, which, remember that number 19?
Yeah, below the threshold for getting non-trivial sets usually.
Exactly. So standard CP, using only those 15 real points, it did maintain coverage, as theory predicts it should. But, just as predicted, the prediction sets were mostly useless, often including hundreds or even thousands of labels, basically saying it could be anything.
Okay, so valid but not useful. What about just using the synthetic images?
CP run only on the synthetic data. It failed coverage completely, which isn't surprising because there was distribution shift between the generated images and the real ImageNet images.
Right, and SPPI, the proposed method.
SPPI was the star. It achieved coverage that was within its theoretical bounds, respecting that safety net guarantee, and it produced much more informative prediction sets that were actually useful.
Nice. Even for image classes where the synthetic images weren't maybe a perfect match, I think the paper mentioned Siberian Husky as a class with significant shift.
Yes, that's a great point. Even with that known shift for classes like Siberian Husky, SPPI stayed within its guaranteed coverage bounds. It didn't fail.
Okay, so the robustness held up.
It did. And for other classes where the synthetic data happened to be a better match, I think lighter was an example. SPPI gave even tighter coverage, closer to the target 95%, and smaller, more useful prediction sets.
So it demonstrated both things, the robustness and the efficiency gain when the alignment happens to be better.
Exactly. It showed both sides of the coin.
Now, what about that other experiment they did, using real images from different classes as the synthetic data? That sounds like an interesting, maybe adversarial test.
It was a neat twist. It really tested that subset selection idea we talked about.
How did they set it up?
They used, again, 15 real points for the target class. But then they took 1,500 images from entirely different ImageNet classes to act as the synthetic pool, a challenging case.
Definitely sounds like distribution shift baked in.
Oh, yeah. Then they used that score similarity-based KNN method to select a subset of 300 of those synthetic points that seemed most relevant to the real 15.
Okay. And the results?
Again, standard CP on just the 15 real points gave trivial sets, especially for stricter alpha levels like 0.01 that technically require even more data. SPPI, whether using the whole 1,500 synthetic points or the selected 300 subset,
yes,
it maintained coverage within its theoretical bounds for both cases. And, crucially, it produced significantly smaller, more useful prediction sets than standard CP could.
And did the subset selection part actually help compared to using all 1,500 out-of-distribution images?
Yes, the paper reported it particularly helped in what's called the label-conditional setting, basically giving predictions that were more accurate or targeted for specific classes while still hitting the overall coverage target. It showed the value of trying to curate or align your synthetic data pool when you can, even if the source is quite different. For overall marginal coverage, using the whole larger set sometimes had slightly less variability in the results, which kind of makes sense too.
More data points, more stability.
Right. But the selection definitely showed benefit for targeted accuracy.
Okay, and they also looked at regression, not just classification. Predicting healthcare costs, was it?
Correct. They used the MEPS dataset predicting healthcare expenditures. They set it up so historical data acted as the synthetic data pool, and a more recent year was the real data, simulating a common time shift scenario. And again, they only allowed 15 real data points per age group. Very scarce.
And the story was similar there.
Pretty much the same story, yeah. Dared CP using only the small real data had valid coverage mathematically, but the prediction intervals it produced had very high variance. Sometimes they were huge, sometimes small, not very stable.
Right. And using only the historical synthetic data.
That lacked formal guarantees, of course. It only worked empirically if the historical and recent distributions happened to align well for a particular age group, which wasn't always the case.
And SPPI?
SPPI, again, achieved coverage close to the target level across the board and provided much more informative, stable prediction intervals compared to standard CP on the tiny real data set.
What's really striking here, listening to these results, is how SPPI consistently seemed to provide useful, informative predictions with guarantees, precisely in those data-scarce scenarios where the standard methods either fall down completely or become practically useless. even when, as I think they showed in an appendix with a different example, the Beaver dataset, the synthetic data was so mismatched that standard CP using only synthetic data failed coverage spectacularly, SPPI still remained within its promised bounds.
Exactly. That robust guarantee in the face of potentially unknown, possibly large distribution shift is truly the powerful takeaway here, I think. It's a real safety net.
Okay, so let's try to wrap this deep dive up. What does all this mean for someone listening, someone who's actually trying to get reliable predictions in the real world when labeled data is a serious bottleneck?
Well, I think the main message is that SPPI offers a principled, theoretically sound way to leverage the abundance of synthetic data that we can often generate now. It allows you to use that data to significantly improve the efficiency of conformal prediction.
Making it work better with less real data.
Exactly. It's effectively a real shortcut to getting useful guaranteed prediction sets or intervals, even when your precious real labeled data is incredibly limited.
And the sort of clever mechanism enabling this is that score transporter idea.
Yes, that's the core technical piece. It effectively translates between the real score world and the synthetic score world, allowing you to calibrate using the larger synthetic set statistics in a principled way.
And the most surprising part, maybe the most valuable part for practical use, is that safety net we keep talking about.
Definitely. The fact that it comes with those worst-case coverage guarantees that hold no matter what the distribution shift is between your real and synthetic data, you get a lower bound on reliability that you can actually trust, calculated based on your data sizes.
That flexibility seems key, too. Being able to adapt or select your synthetic data, try to make it better, while still keeping that fundamental guarantee.
Yeah.
You're not penalized for trying to be smarter about your data.
Exactly. You don't risk the fundamental promise just by trying to improve efficiency.
So, summing it up, SPPI gives you a pathway to more informative predictions in these tough, data-scarce settings. It offers some surprising facts, like those robust guarantees independent of shift. And fundamentally, it helps you avoid that feeling of being overwhelmed by needing huge amounts of perfectly matched labeled data. It shows you how to leverage alternative data sources, like synthetic data, effectively and rigorously. This definitely raises an important question to maybe leave our listeners pondering, though. The paper's formal guarantees, as you mentioned, rely on that assumption that your small, real calibration data and your new test point are exchangeable, basically drawn from the same underlying distribution.
Yes, that's a standard assumption for basic conformal prediction, too.
But what happens in the messy real world if that assumption isn't perfectly true? What if there's some drift or shift between your real calibration data, collected maybe last month, and the future data you'll actually apply the model to next month?
That's a really critical question and a known challenge in making reliable predictions generally. The paper itself points towards extending this SPPI framework to handle those kinds of shifts non-exchangeability between calibration and test data as an important direction for future work. There are existing techniques for handling that in standard CP that might be adaptable.
So how might that potential extension impact the kinds of real-world scenarios where you could ultimately deploy SPPI? Or, maybe stepping back even further, how could you think about applying the core ideas of SPPI, leveraging different data sources with guarantees in a setting where getting any labeled data, whether it's real or synthetic, is just incredibly challenging to begin with?
Interesting thought, yeah. Definitely something to chew on after our dive today.